time to do some practice involving sequences. In other words, we have our list of numbers, and we're trying to understand them. And in particular, what we're really trying to understand is what's happening at the end, the tail, so to speak. So in other words, if we were able to walk and pick up the very last term, what would it be? Of course, because infinity is involved, there is no last term. So when we talk about going to pick up the last term, what we really mean is, what should it be? So that's what we're after. As with anything, it really takes practice to get good with it. So make sure you're doing as much as you can. If you're following along, make use of the pause button. If you see a problem, try it yourself first and see how far you can get. And if you ever need any help, no problem. I'm here, just unpause. And then we can work it out. Well, let's begin. Our first problem. Let f of x equals sine pi x and a sub n equals f of n. Find the limit as n goes to infinity of a sub n. Now, what's going on here? Well, you have this function, sine of pi x. And so, what do you see? Well, what we have is sine is oscillating. It goes up and down. So we're going to go up and down infinitely far as we head off, right? And now, if we think about our function as a function of x, in other words, continuous, what's the answer? Well, if we're going down and up infinitely often, well, it's not going to converge to anything, right? But here's the distinction. We don't have to think of our function as being a function of a continuous variable. And what's going on here is when we talk about this notion, this concept here, what we're really thinking is we're doing some sort of sampling. In other words, we're only looking at the places where we're at the integer values. 1, 2, 3. And the gaps in between, we don't worry about. So what happens? Well, sine of pi, that would be when we plug in 1, is 0. Sine of 2 pi is 0. Sine of 3 pi is 0. And 4 pi, and 5 pi, and so forth and so on. So what happens is that when we sample, we say, oh, even though the function from a continuous perspective is going up and down, what we really have is, aha, a sub n is 0. And so our limit as n goes to infinity of a sub n will also be 0. So this is a demonstration of the difference between saying, oh, looking at it as a continuous versus looking at it as integers points where we sample. There can be different types of behavior. In one case, the limit doesn't exist. In one case, the limit does exist. So just as a word of warning, be careful. Now, you might say, well, what if we had changed our function? Suppose it had been f of x equals sine of x, and a sub n equals f of n. Then what would have happened? Well, we would have still sampled, but it turns out that in this case, what ends up happening is that when you sample every 1, you get something rather chaotic. It jumps around. Because what's happening? Well, sine is periodic of period 2 pi, right? It repeats every 2 pi. But what you see here, of course, is 2 pi and 1 don't really get along well. So you sometimes might be close to 0, sometimes might be far to 0, and so you don't really know. In fact, it turns out in this case, there would be no limit. The limit would not exist. So be careful. Things matter, and pay attention to the function. So, all right, well, that wasn't so bad. Let's keep going. Hopefully they're also not bad in the future, right? That would be nice. Let g of x equal x squared over e to the x, and a sub n equals g of n. Find the limit as n goes to infinity, a sub n. Now, previously in the last problem, we said, oh, the function that we're looking at, sine, it doesn't really converge. So don't be misled. Now, here's the thing. If the continuous function converges, the sampled function converges. If the continuous function doesn't converge, kind of all bets are off in some sense, because it just depends on, hey, where did you look? Now, so don't discount, oh, let's look at the continuous part and ask the question. So here we say, well, let's just say what happens here. When we take the limit as x goes to infinity of x squared over e to the x, so here I'm thinking about as a continuous function. Well, it's currently going to a large number over a large number. Aha! Which means more work. More work. Right. Good. So we do more work. Now, the best way to do more work here is to take advantage of l'hôpital. Ah, l'hôpital, mon ami. All right, so what does l'hôpital have to say about this? Well, this is the limit as x goes to infinity. All right, take the to the top over to the bottom. All right, now, here we get infinity over infinity. Aha! More work. Yes. Okay. Well, but we're optimistic because in some sense this is simpler, right? We started with a quadratic on the top. Now it's down to linear. That's simplifying. Okay, let's keep going. So we do more. Ah, l'hôpital, mon ami. So it becomes the limit. X goes to infinity of 2 over e to the x. Well, that doesn't go to infinity over infinity. It goes to 2 over infinity. In other words, 2 over a big number, which is 0. Now, if the continuous function converges, then the discrete variation, the one where we sample, also converges. Because this says, look, all the values of x are getting small. It doesn't matter. And so the values of x, where we're just looking at the integer values, also is going to get small. And so the answer is 0. Wow, lots of zeros so far. Well, that's all right. We'll probably have some non-zero answers at some point. I hope, but might be a while. Okay. So, our next problem. Show 1 over n, which is a sequence, where for every term we take 1 over the nth number. We start at 1 and go to infinity. It goes to 0, all right, using the limit definition. Now, here we're going to use the limit definition of sequences. So, okay, so what do we have? Well, recall we need to show that we say the limit as n goes to infinity of a sub n equals L means what? Well, for any small epsilon, so epsilon is measurement of closeness. Keep that in mind. So closeness of what? Well, closeness between the a sub n and the L. So that's what the epsilon measures. There is some capital N, which depends on epsilon. So in other words, how close I want to get will force how large I have to look. So that if I'm bigger than this point, if n is greater than n epsilon, then the difference between a sub n and L is less than epsilon. Another way to think about it is we're really saying, hey, if we're getting close to infinity, where closeness to infinity here gets measured by saying you're a large value. So as we get close to infinity, the difference between our sequence and our limit is very small. Okay, so that's the definition. So we say, okay, let's start with this and try to figure out what our n of epsilon should be. So we know what our a sub n is. It's 1 over n. We know what L is supposed to be. It's supposed to be 0. So we want 1 over n minus 0 to be less than epsilon. And now the question is, how should we choose n? Now the nice thing is, minus 0 doesn't do anything. Absolute value doesn't do anything. So we can say, okay, or 1 over n has to be less than epsilon. And now we say, all right, flip both sides. So I'm trying to solve for n. Now if you flip both sides, your inequality is going to reverse direction. So we say, this will be true if n is greater than 1 over epsilon. And now we say, hey, we're looking for n greater than something, which depends on epsilon. So this part right here, this is our n of epsilon. And now we say, perfect. You see, the way that you prove a limit is to say, you give me an epsilon, I can give you this function, this n epsilon, which tells you how far down you have to look. And now, this tells us exactly how far down we have to go. It says, if you want to be within 1, okay, just start at 1. If you want to be within, say, 0.01, 1/100th, it says, all right, go to 100. And past that, you're closer than 1 over 100, and so forth and so on. So that's just a very, very simple example of what's going on, but it gives you a flavor for these types of problems. All right, well, that's the basic idea. Good. Let's do another problem. Find the limit as n goes to infinity of a sub n, where a sub n is what? Well, it's cosine n divided by n. All right, now what can we do? Well, we could say, hey, what's happening here? If we think of this as a continuous function, we say, oh, look, cosine of n, as n goes to infinity, it doesn't converge because cosine oscillates, keeps going up and down. So if I take a limit as I go to infinity, I get a does not exist over infinity, which means more work, but not the kind of L'Hopital more work. So what can we say? Well, here, what we can say is say, and this is a common thing that we'll see. When you see a cosine or a sine, sometimes what's happening is it's acting like noise. And like, okay, so this is noise. All right, let's see if we can figure out how to sort of learn to ignore the noise. And how do we do that? Well, we say let's replace it because cosine and sine are bounded. They can't get arbitrarily large, they can't get arbitrarily small. They oscillate between two values. And so, it's a really important thing to remember. We know that cosine is at most 1. So, this is at most 1 over n. And the smallest it can get is negative 1. So this is above negative 1 over n. And yes, you are allowed to have negative values in sequences. There's nothing wrong with having negative values in your sequence. So we say, okay, this cosine n over n, that's not easy to deal with directly, but by controlling, or rather using the fact that it's bounded, we can get it in between two things, which are nice. And now, here's our idea. We're really using our sandwich theorem. And what do we get? Well, 1 over n goes to 0. Minus 1 over n goes to 0. We actually have that, right? In fact, we have it rigorously proved that it goes to 0. And therefore, this also goes to 0. I guess I should say another name you might see for this is the squeeze principle. So our conclusion is the limit as n goes to infinity of a sub n is 0. All right, nice. Cool. All right, well, let's try another problem, right? Okay. Let a sub n be the square root of n squared plus 4n, and b sub n is minus n. All right, and what's the question? Find the limit as n goes to infinity of a sub n plus b sub n. So I have two sequences, a sub n, and if we look at it, what's happening? It's getting pretty large. It's getting bigger, 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 bigger. b sub n, it's also getting pretty large, but negative, smaller, 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 negative. All right. So this is really going to like infinity minus infinity. Aha! And infinity minus infinity, based on all the problems we've seen so far, right? Our interest has been 0. So is infinity minus infinity 0? No! Infinity minus infinity is more work. See, it's ambiguous because I say, well, look, yeah, they're big, but how do they differ? All right, so time for us to do some work. Well, let's see, what can we say? This is our limit as n goes to infinity of square root n squared plus 4n and minus n. Okay, now generally speaking, the way we like to do problems where we have like indeterminate, things like infinity minus infinity, is we prefer ratios. Because two things can happen with ratios. One thing is you can do l'Hopital, but the other thing you can do is you can, what I like to call, pump the brakes. Now, pump the brakes, this is for old-fashioned cars. Don't do it with modern cars. Modern cars, actually, you should not do it. But the idea is that in old cars, you would say, hey, if the car is not slowing down on like an icy road, by pumping the brakes, it would help the tires do a better job of grasping and help you control the vehicle. In other words, it would help you slow down. So when I talk about pump the brakes, it really means slow it down, slow it down. And you can do that when you have a ratio, but you can't do it when you have only a sum. So we say, great, well, how do we get to a ratio? Well, here we say we can multiply by something, and we say, well, let's also get rid of a square root. If we're multiplying by something, a great candidate is the conjugate. So I'm going to multiply by square root of n squared plus 4n plus n, and downstairs square root of n squared plus 4n plus n. Now notice I'm multiplying by 1. Okay, so we're fine. We haven't changed anything. No worries. So what does this become? Limit as n goes to infinity. Well, we'll see when we multiply here, we'll get a squared minus b squared, because that's why we multiply by conjugate, a minus b, a plus b. So it'll be n squared plus 4n minus n squared on the top, and downstairs, well, square root of n squared plus 4n plus n. Now, some good news, the n squareds cancel. And at this point, like, perfect. Now we're going to what? Well, the top is getting huge, and the bottom is getting huge. And I know you're like, oh, let's do l'Hopital. But look, not everything is l'Hopital. In fact, it's really simple to see what's going on. You say, hey, what's driving the growth on the top? Because if you look at it, they're more or less just algebra here. Like almost, it's not really a polynomial, but kind of polynomial-esque. You say, look, the rate of growth on the top is n. So we're going to slow that down so it doesn't go large, and we don't want it to go to 0. So we say, okay, multiply by the reciprocal, 1 over n. So if we're going to multiply top and bottom by 1 over n, well, what would be the effect? So imagine timesing by 1 over n. Well, what will happen is on the top, we'll get the following. 4n times 1 over n is 4. Downstairs, well, we have the n times 1 over n. That's the easy one. That's 1. And now, what do we do with this 1 over n in the square root? Well, it turns out we can be careful. Is it true that n is the square root of n squared? Is it? Now, if you answered yes, I would accept it. And if you answered no, I would also accept that. Technically, the answer is no, it's not true. Why is it technically not true? Well, it's because it should be absolute value of n. But why would we accept yes? Because where are we letting n go to? We're letting n go to infinity, positive infinity. So we can think of n as being a positive value. So for us, for our purposes, we're okay with just using n. So what does that mean? That means I can really move this n inside that square root as an n squared, but it'll be underneath. And so if you move it in as an n squared, and then divide each term, you get 1 plus 4 over n. And now we say, it's easy to see what happens because there's only one place where n shows up. It's right there at the 4 over n. And we know what happens as n goes to infinity, 4 over n gets small. So we say, hey, this goes to 4 over square root of 1 plus 0 plus 1. Well, that's really 4 over 2, also known as 2. So it turns out that these two sequences, even though they both get large in magnitude, the relative size, it's almost identical, off by 2. All right. Wow. Amazing. Amazing. So in some sense, by the way, now that we see the answer, we could have said, oh, you know what? It kind of makes sense. Because go back to this square root of n squared plus 4n. Now, it's not a square because of plus 4n, but suppose we were to complete the square, plus 4. Now, you should justifiably say, you can't just complete that. Well, okay, so we'll add and subtract. That's adding 0 on the inside. So that would be the same as the square root of n plus 2 squared minus 4. And now we say, hey, when n is large, the first term completely dominates. You know, if n is 1,000,000, this minus 4 is nothing. It doesn't really matter. So this is very, very close to the square root of n plus 2 squared, which is n plus 2. So that's why we say, oh, so this is really close to n plus 2, and that's really close to minus n. In fact, it's exactly minus n. And so when we put them together, we get 2. Well, of course, in retrospect, everything seems obvious, right? Why can't we start our answers once we know what the solution is? Well, that's not how problems work, right? If we knew what the answer was, it wouldn't be called a problem. So, all right, well, good. Let's keep going. Another problem. So, let an be the recursively defined sequence where a0 equals 2, and for n greater than or equal to 1, we have an equals 72 over 1 plus a sub n minus 1. And it says, okay, write down a1, a2, a3, and a4. It says you do not need to simplify your answer. Oh, okay. Phew. All right, let's do that. All right, so we know what a0 is. So a0 is 2. So a1, according to this, would be 72 over 1 plus 2. Now, we don't have to simplify our answer, but if we can, why not? It doesn't say we can. So that's the same as 72 over 3. And it turns out 72 does divide into 3. It's 24. Okay. So a2 would be what? Well, 72 over 1 plus, see, that's the rule, right? 72 over 1 plus the previous term. That's what we mean by recursive. You build off of the previous case. So in our case, the previous case is 24. All right? So that makes it 72 over 25. And, that doesn't simplify. All right. Well, a3 would be what? 72 over 1 plus the previous term. 72 25ths. Well, we could try to simplify it, but we don't have to, right? And then what is a4? So a4 would be 72 over 1 plus the previous term. Okay, which is 72 over 1 plus 72 25ths. Okay, so there we go. A1, A2, A3, A4. And you can see, oh, it's getting pretty messy there. Uh-oh. Uh-oh. All right. Now, step 2, part 2. What do we have? Well, we're told, look, the sequence converges. We don't have to prove it converges. We're just given that it converges. What does it converge to? All right. So we have to find the L. So the A sub n goes to L. And now, what can we say? Well, we look at that, and we could be like, well, one way to do it is we can try to do a lot more patterns, a lot more numbers here, hopefully see a pattern, prove it. Kind of hopeless, right? We were kind of stopping after we got to A3. A100, what? No, forget it, we'll never get that. But what we can do is say, all right, what would have to be true? Well, what would have to be true is we say, as n gets large, what happens to the two sides? Well, the left-hand side, we know that A sub n is going to L. So there we go. What about the right-hand side? Well, what do we have? It's going to 72 over 1 plus. Now, what does A sub n minus 1 do? Now, let's be careful here. So we're starting, and we're going down, and we've gone a long ways. Here's A sub n. It's close to L. Now, A sub n minus 1 is just right behind it. So if this is close to L, what is this close to? Also close to L. Because the idea is all the terms at the end are getting close to the same thing. So that's also going close to L. And we can say, aha, since that side goes to L and that goes to 72 over 1 plus L, they must be the same. So what we're getting is the relationship that our limit has to satisfy. Well, all right, multiplying across, we say, okay, that says L plus L squared equals 72, or L squared plus L minus 72 equals 0. And we say, can we factor? Are there two numbers that multiply together to give us 72 and sum to give us 1? Well, turns out L plus 9 and L minus 8, that should do it, right? Because 9 times 8 is 72. And then 9L minus 8L is a single L. And we say, so we seem to have two candidates. One candidate would be if we let L be negative 9, and the other candidate would be if we let L equal 8. Now, we can't have two limits. So one of these is right, and one of them is not right. Well, think about our sequence. If I start with a positive number, I'll have a positive number. And we are starting with a positive number. We're starting with 2. So, what does that mean? Well, it means that all my terms that I'm going to generate are positive. So if I'm approaching anything, I have to approach the positive possibility so we can toss negative 9 out. And therefore, we come to the conclusion that L equals 8. That's the limit. That's good. All right. Good stuff. Fun problem. Fun problem. Well, on to the next one. I think we have time for one more problem. One last problem to finish it up. Let the sequence A sub n, where we go 0 to infinity, be defined by A0 is 0, and AN is root AN minus 1 plus 2. Show that the sequence converges by showing AN is less than or equal to 4 and that AN is monotonic. And of course the question is, what does it converge to? All right, well this should be interesting. So we want to prove it converges because we're going to show it's monotonic, which means it has one behavior, either always going up or going down, and it's bounded. Monotonic plus bounded says you must converge to something. And then we have to say what it converges to. So let's think about this. Now, how can we make this argument? And it turns out that both parts were saying, we have to stay bounded by 4 and that we have to be monotonic are both going to be done in the same way. Namely, look at our sequence. We have a sub n, which is the square root a sub n minus 1 plus 2. So I can think of this in the following way. I can think of this as a sub n. It depends on the previous term. So I can think of it as whatever the previous term is, there's some rule, also known as function, which gives me the current term. Now the question is, what is this function? Well, it's the function where f of x equals square root of x plus 2. So what we need to do is understand this function. Now, the good news is we can understand this function. Let's see, it starts here at 2, and we only care about what happens up to 4. Now, note that the square root of 4 plus 2 is indeed 4. And so it's going to hit here, and it looks something like this. Okay, so there's our function. There's f of x. Now, how do we argue that it is monotonic? Well, here's the key. Look at our function f. F of x is monotonic, which means that, for 0 less than or equal to x less than or equal to 4. In other words, we're going up. So, see, going up. So what we can say, in fact, it's true for any x because it always keeps going, always keeps going up. So that says, look, a sub n, which is our function of a sub n minus 1, has to be greater than or equal to a sub n minus 1. Now, I'm going to backtrack here. It's not, we don't care that the function is monotonic. What do we have to say? We have to say the function a sub n minus 1 is greater than or equal to a sub n minus 1. Now, where does the function look at? So what do we want to compare? This we can think of as f of x versus here x. Well, where is x in the diagram? Well, the answer is it is right there. So, since we see for 0 less than or equal to x less than or equal to 4, that f of x is above x, that says, hey, if I look at some point, I'll call this a sub n minus 1, then that value here would be a sub n minus 1, while this value up here would be f of a sub n minus 1, which is also equal to a sub n. So you see, we have the curve here is above the line, so a sub n minus 1 is below a sub n. So that is why we have monotonic if we stay between 0 and 4. So we know we start at 0. Now we have to argue, well, why do we not go above 4? And now is our great, look at the picture moment. Notice that if we have 0 less than or equal to x less than or equal to 4, well, what's the range? The range of our function f of x, which is square root of x plus 2, is going to be between 2 and 4. So, what's the moral? It says, hey, if you plug anything in that's below 4, the output is below 4. So, what this says is we say, aha, our great moment of insight. So if we start below 4, we stay below 4. And that's what we need to say, because we are supposed to show, hey, this is bounded. If we say we can always be below some point, then we're bounded. So we say, perfect. So we are bounded by 4. So we've now said what? We know we're starting below 4, and we say, look, as long as you start anywhere below 4, your output is below 4. In other words, your a sub n, your next term, is at most 4. And it says, look, as long as you're below 4, you're still below 4. And so we must be bound. We have to be bound by 4. Now, the last part. What does a sub n converge to? Now, we could go through a process similar to the last problem. We say, oh, well, we'll call this L, we'll call this square root of L, and we'll call this 2. But let's do the picture, because I think the picture is cool. So what does the picture argument say here? Well, what the picture says is, where do you start? You start at 0. So there, we're starting at 0. And now you plug it in, and when you plug in, you go up to the function, and now you say, okay, where are you at? Well, the answer is you're at 2. So now, if A0 is 0, A1 is 2. Well, now what do? Now you plug it into the function, okay? And we go up. All right, so now we're up to 2 plus square root of 2. Okay, well, where does that fit in? Well, go across to the line, and it fits in here. So we're just stepping our way, and now we repeat. So what happens is you're going to, step up, and you see where are we going to as we go in? We're going to the intersection. Where does the line intersect the curve? And where is it? It is at 4. So we say, aha, a sub n is converging to 4. Now, if you don't like that argument and you say, well, I'm not sure I'm convinced by the geometric picture, you can still do the same type of analysis. Yeah, you say, okay, look, a sub n is the square root of a sub n minus 1 plus 2. That goes to L. This goes to square root of L plus 2. Whoops. And now we say, all right, square both sides. Not square both sides yet. Move the 2 across. L minus 2 equals square root of L. Square both sides now. L squared minus 4L plus 4 equals L. And then we get L squared minus 5L plus 4 equals 0. And we come up with the conclusion that L is either 1 or 4. Right? And that's how it factors. Well, which one is it? Is it 1 or is it 4? And the answer is, it's 4. And so there we go. All right, well, there we go. That's an example, very, very simple example of a sequence which is monotonic. And here we're really just saying, if we can understand what the function is doing, it really gives us insight into what the overall behavior is. Well, thanks for coming along. Hope you enjoy the problems, and hope to see you again. Bye.